Hello everyone, this is lecture 4 of week 12. So, recall that in the previous 3 lectures we learnt about supervised learning problem and had the simplifying assumption of linear relation between the feature vector and the label data, and we used the square error, right. And in the last class we actually implemented the OLS algorithm, right, the ordinary least squares algorithm. So, if you recall what the work was, right, the code was, right, it was more of importing the data and processing the data rather than anything to do with optimization algorithms, right, whatever we had learned in the past 11 weeks, right. So, that is expected because we know the closed form solution, right. But for ridge regression we do not know the closed form solution, right. So, we will implement that in this lecture. Okay. So, given that we have I mean in the previous code we have already imported all the data, process the data and everything. Okay. So, it just remains to implement the ridge regression algorithm. Okay. So, we will do that. So, recall that in ridge regression we have a constrained optimization version as well as an unconstrained optimization version. Okay. So, we will start with the constrained optimization version. Okay. So, the objective function is summation I equal to 1 norm yi minus beta hat minus summation beta j hat x j the whole squared, right. So, fine, we will define f of x g of x as we do any constrained optimization problem. Okay. So, fine, so we have not named these codes. So, for this we will name it as ordinary least squares, which is OLS, right. Yeah, and for this we will call this ridge regression constrained version. Okay. So, okay, all right, written it as a text. I wrote it as a code, unfortunately. Yeah, okay, and I did the same error here. Let us correct that as well. Okay. Yeah, this is going to be text. Yeah, fine, all right. Okay. So, let us define f of x. Okay. Sorry. So, this is going to be something very similar to this. Okay. But instead of testing data, so the test data is what we do it finally, right. So, but for the training data the minimization is actually going to happen on the training data, right. So, I will change this as train, and so instead of beta, I mean beta is how I wrote down the theory, right, when I wrote it down on the screen, right. But nevertheless we write the code in terms of x. So, we will write this as x itself. Okay. And this I can write this as x train, okay. Not a problem. I mean, so I have just written down the objective function. Okay. Fine, and we will write down the constraint as well. Constraint is just beta 1 squared plus beta 2 squared plus dot beta p squared. So, since we are writing beta as x, right. So, this is going to be x of 1 to p, that is dot x of 1 again minus s. Okay. So, s we have not defined as yet, we will do so shortly. Okay. And we also have to define the gradient grad g of x. Okay. So, that is actually, I mean, so x of 0 has to be included. So, that is 0, and for the rest it is just 2x, right. So, we will insert 0 into x. Okay. So, this is just 2 into x 1. In this you are going to insert 0. Okay. So, actually we will write this as an array, that will be helpful. Yeah. So, in this array we are actually inserting 0 in the beginning. Okay. So, that is all is grad g of x. Okay. So, note that for constraint optimization we have two algorithms, one is the augmented Lagrangian method and the other is the quadratic penalty method, right. So, here we will start with augmented Lagrangian method. Okay. So, fine, yeah, we have the code in front, right. So, let us pick it from there. This is quadratic penalty method, yes. So, augmented, but this is for equality constraints. What we have is an inequality constraint, right. Yes. So, here, yes, we will just use this code as such, start from here, we will copy this down and use it straight away. Okay. So, let us check if things are fine. Yeah. So, Lagrangian is just f of x plus gamma into and then you have a minus summation mu squared by 4 gamma squared as well. Okay. And then you have the gradient. Okay. So, we can remove this since it is not required here. Okay. Yeah. So, yes, this is gradient of f of x. So, gradient of f of x is okay. So, this has to be okay. I think we need to write okay x train with a 1 in front. Okay. So, that I think we have used h already. Okay. So, yeah, the other way of writing this is h into x. Okay. So, maybe I will do it that way because yeah, that is possibly much better. I mean it is easier to write down the derivative and the Hessian. Okay. So, I am just changing this as h into yeah x, I think that should be fine. Okay. So, I mean if you are asking what I am doing here, I am just right. Yeah. So, I have just written y minus h beta transpose y minus h beta to be precise, right. So, that is actually norm of y minus h beta the whole squared, right. So, yeah, this is y minus h beta norm squared, that is why you have np dot sum and squared and all that. Okay. So, the reason why I wrote this is when you differentiate this with respect to x, that is take the gradient, I can write the answer very easily, right. So, it is minus 2 into h transpose at y train minus h x. Okay. So, and now here we need to write okay. So, the Hessian part should come in the beginning, right. So, the Hessian is 2 into h transpose into h. Okay. And so, yeah, this part is I mean I do not know if you how many of you recall this 2 gamma into del g transpose, and that works when g of x plus m by 2 into gamma greater than m by 2 gamma is greater than 0, right. And you need something of this sort for the I mean g of x into the Hessian of g of x as well. Okay. So, maybe I will pick that page, should be somewhere here, it is this that we are writing. Okay. We only have one inequality constraint, right. So, all the h can go out. So, you should have del 2 f of x, del 2 f of x is what you have here 2 into h transpose h. Okay. Yeah, for 2 gamma you have this max of 0 g of x plus mu by 2 gamma, right. So, that is this part into del g of x del g of x transpose, that is one. And the other one is the Hessian, right. So, the Hessian of g is something that I have to write. Okay. So, let us do that. Yeah. So, this has to be okay. Yeah. So, since you need g of x plus m by 2 gamma greater than or equal to 0. So, I will include this here as well. Okay. So, you will have this part here as well, and you will also have this again. Okay. So, this is max of 0 comma g of x plus m by 2 gamma, nothing fancy. Okay. And what is the Hessian of G, right. So, it is a diagonal matrix with 2 everywhere, but only at the first value it is 0, right. So, it is a diagonal matrix with 0 and 13 2. So, it is a 14 cross 14 matrix, right. So, 14 cross 14 matrix where the first 14 cross 14 diagonal matrix where the first diagonal is 0 and the rest is 2. Okay. So, I will write that here. It is np dot, maybe you do not need this, yeah, np dot diag of, yeah. So, it would have been nice if we were able to write it as 14 of them, but now you will have to insert. Okay. So, we will insert a 0. Okay. So, with this at 0 I am inserting a 0. Okay. Yeah, maybe if it is not nicely readable, I will yes, write it this way. Okay. Yeah, this is possibly a little readable because, so what I have written, so this is max of 0 comma g of x plus mu by 2 gamma, right, and this is so this part is 0 comma 2 times, right, and yeah, you are just forming a diagonal with that. Okay. All right, and now you should also change the initial value x. I will, so yeah, this is actually a 14 dimensional x, right. So yeah, I will just pick it as 20 ones. Okay. Sorry, 14 one, it is actually 20 20 20 14 times. Okay. So, I am just picking some large value. Okay. And you only have one constraint. So, let us pick that to be 0 and m can be 1, no problem, and yeah. So, gamma is yeah, sorry, gamma is 1, no problem, and k is fixed to be 0. Okay. All right. Yeah. So, the rest of the code has no problem. Yeah, we will disable the prints because there could be a lot of iterations. Okay. But the rest of the code is the same. So, we still have one more thing to accomplish, which is the value of s, right. So, yeah, I mean this actually needs some work. Okay. But since I have done the work offline, okay, so I will just give the give a particular list, okay, which contains I mean the right answer roughly. Okay. So yeah, I will write down the list of s to be the following. Okay. So yeah, this will have 0.1, 0.2, 0.5, 1, 2, 5, 10 and 256. Okay. So, we are going to run this code for all values of f, all values of these s whatever I have written. Okay. And we will choose the one that has the minimum testing error. Okay. Fine. So, since I have to run for all of this, so I will run it as the following. So, this is len of s. Okay. And s is equal to s list of I. Okay. And I have to do the indent now, change the indent rather. And yeah, so after you finish this, yeah, we will print the value of s and the testing error, because that is finally what we need, right. So yeah, but instead of beta it is the x what we have found at the end. Okay. All right. So, let us so this is basically the code. I mean if you want me to spend a minute running over it again. So, I have defined the function objective function to be minimized, right, and yeah, the constraint is x1 hat squared plus dot 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 xp hat squared less than or equal to s, right, and the gradient is gradient of g. I have defined the Lagrangian function, the augmented Lagrangian function, the gradient and the Hessian. Okay. And since we do not know what this value of s is, I am giving a list of s and we are going to check for each of these values. Okay. So, let us see okay. oh sorry, it's S list. Okay, there is one more error. Okay, so there is a small problem. The issue is I am using H and H I mean two places. So, I should change the name of this. So, sorry for that. So, let me call this capital A maybe. Okay. So, I mean since this is this is the easier one to change, I am doing that. Okay. Okay. So, I should first run this and get the same answer and just change the values of sorry the variable capital H as capital A. Okay. So, wherever it is there, yes, I suppose I have changed it everywhere. Yeah, otherwise anyway it will give an error. Okay. So, there is again an issue. Oh, okay. So, this should be A. I am sorry. Okay. So, this may take a few seconds before completing. Okay. So, let us wait. We ran the code and yeah, so here is the answer. So, I have made a few changes. One of them is that, so we usually fix the tolerance as 1e minus 6, right. So, since the we are running on a big data with 400 data points, right, and also for many values of S. Okay. So, I increase this to 100. Okay. Yeah, you can give this as 1e minus 6, it will take more time, but the answers will not be very different. Okay. So, you can see that when you give S is equal to 0.1, right, the test error, right. So, which is I mean similar to what we computed here, right. So, here we computed it to be 4016 point whatever, right. So, when we give S is equal to 0.1, we get an error of 1726.8. When S is equal to 0.2, we get 1639.04, and similarly for 0.5, 1, 2, 5, 10, and so 256 was given on purpose because you can see that we are getting the same answer. So, this is 4016.74 and this is also 4016.74, right. So, the reason is that okay. Yeah. So, note that if S is actually greater than yeah. So, I will write that if S is greater than or equal to beta hat 1 squared, I mean, so for the OLS plus beta hat 2 squared for the OLS and so on, plus dot 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 plus beta hat P OLS, right. Then this condition that you have here, beta hat 1 squared plus dot 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 plus beta hat P squared less than or equal to S. Okay. So, that condition actually becomes redundant, right. So, because you just put OLS and I mean even without the condition the constraint is actually satisfied, is not it. So, I mean that was the reason I gave a very high value of S. Okay. So, which is 256 in this case, right. So, yeah, you can I mean if you want me to compute yeah, this one beta 1 dot of beta 1, right. So, that is what is beta 1 squared plus dot 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 plus beta p squared, right. So, that is 254.58. Okay. So, I just wanted to give something higher than that. So, I gave 256, right, and so you can see that you are getting back the answer, right. The most important thing to note is that when we used OLS, the testing error was 4616, right, but when we use ridge regression, the test error drops drastically, right, from 4000 to 1600 odd, right. So, yeah, so the value that we are looking for is actually s is equal to 0.2, right. So, that is how we have, because yeah, you can see that it starts at 1726, it decreases up to 1639 and then increases further, right. So, you can check with more values as well. So, since I have worked this out before, I mean I am able to give you the right value of S in this case. Okay. So, in fact, I could have worked this with the respective value of M. Okay. Maybe let me do that, so that I mean I will tell you why this is essential. Okay. So, yeah, this may take a minute or two. Okay. So, I included this M, that is the mu value, and yeah, I have also got the mu value for each of the value of S, right. So, yeah, I will tell you why this is important, okay, maybe slightly later, but note that for each of the value of S, okay, we got the corresponding mu value that is printed, and also the testing error. Nevertheless, the I mean it is the least when S is equal to 0.2, 0.2, okay. All right, and we will run the same code with, so this is, we have got the answer for ridge regression using augmented Lagrangian method, right. So, we will get the answer now with quadratic penalty method, okay. So, the function and the constraints are the same, okay. So, the rest of the code will change. Nevertheless, we have the code right here. So, these are for equality constraints. So, we will go for inequality, yeah, the one with inequality constraints. So, here is it, this is the, yeah, so here is the code, and so we will just run this for 0.2, okay, because yeah, we know that it is, this is the lowest, right. So, and we just want to see whether quadratic penalty method also gives us the answer, right. So, we will just do this. So, we have f of x plus gamma into g of x plus the whole squared, right, that is the q function, right. And yeah, so del f and del 2 f needs to be modified as given here. Let us do that as well. So, this is minus 2 a transpose and so on, and here you have this minus 2 a transpose into y train minus a x, and here you will have yeah, 2 into a transpose a, and this you have, and again you will have the third part. So, this is the one corresponding to gradient of G, gradient of G transpose. You should have one with that corresponds to the Hessian of the constraint G, right. So, yeah, that will be similar to this. I will write it down nevertheless. I mean I will copy it and then modify it as required. Sorry. Yes. Yes. So, this is just g of x and not all of these things. Yeah. So, if you remove that, I think yeah, it is just the same. So, it is just g of x greater than or equal to 0 and the same matrix that we want to have, right. And so, here again I will modify this maybe to 1, okay. And yeah, so x needs to be changed, x is just ones of 14, right, okay. And yeah, we will remove the prints because yeah, so this is what will be required, and we will print the yeah, so I will just copy down the command from here. Okay. So, yes, we will run the code. yeah, okay. So, S needs to be modified as well. S is 0.2, okay. And here we will print gamma instead of mu, okay. Yes, okay. So, for 0.2, yes, we have got around about the same answer, 1641 instead of 1639, right. But one thing that you need to note is that the value of gamma is huge again, it is about 536 million, right. So, yeah, in Indian system will it is like 53 crores, right. So, yeah, I mean we usually get answers, the right answer with very high value of gamma, right. So, here as you can see it is yeah, like 5.36 into 10 power 8, that is where you get the right answer, and that too after modifying tolerance to be 1 instead of 1 e minus 6, right. So, but nevertheless that's because the problem is just too huge, right. So, with some amount of modifications we are actually able to solve for both solve this constraint problem with I mean using both augmented Lagrangian method and quadratic penalty method, right. So, in the next lecture, which is going to be the final lecture of this course, I will also solve for the unconstrained version, right. So, in these 4 lectures I have I mean explained an application and I mean solved this a constrained optimization problem using both constrained optimization algorithms that we have learnt for nonlinear programming, right. So, in the next lecture I will work for the unconstrained version as well, okay, and also let you know about a few more commands how to carry on with optimization if you are actually using Python to solve an optimization problem. Thank you.